Now, this new concept is something you have to stop and read a few times to make sure that you understand the idea behind this. So, the thing that we had to sort of grasp in the previous video was how different it was to see that 1 over n, this as a series diverges, but all of a sudden, if you allow it to alternate, it will converge. So there are other series that behave that way, and the series that behave that way, we call them conditionally convergent. So this series right here on the right, if you don't take absolute values and you allow it to converge and allow it to alternate, it will converge. But if you take absolute values of each term separately, you go back to the harmonic and then you make it diverge. So for these kinds of series, you call it conditionally convergent. So the alternating harmonic series is conditionally convergent. Let me go ahead and read this with you. Whenever you have a series that on its own, on its regular format, it converges, but if you take absolute values of each term separately and create a new series, then that series diverges, then you're going to say that the series that you have to begin with was conditionally convergent, meaning it converges on the condition that you don't take absolute values of the terms. It's still convergent, right? So this is just a new concept in comparison to what we saw before. Now, on the other hand, if the series that you had, the original series that you had converged, so this guy converged, you take absolute values, and then the series continues to converge, still converges, so your new series that you get after taking absolute values, it also converges, then you say that your series is absolutely convergent or that it converges absolutely. In some books, including Stewart's Calculus, the definition is not the same as this that I'm showing you now. This definition is slightly different. In Stewart's Calculus, the book will say that the series is called absolutely convergent if this condition is verified. If this converges, if the second series converges. You don't really need to check this because of the theorem that I'm about to show you. If you have a series, you take absolute values of each term separately, and after doing that, you end up with a series that converges. Then you don't have to check the original series to begin with, because that will also converge. And this is a theorem, so this has a proof. I'm not going to prove it formally to you like I never do with epsilons and deltas and everything, but I can give you a very solid idea using the tests that we already know. For example, you can see that it is always true that the absolute value of an is greater than or equal to an, because if an is positive, these are equal, right? And if an is negative, of course, the positive side is going to be bigger. So this inequality is correct. And also, this is greater than always negative absolute value of an like this. So stop again to think about this. This is for sure negative because absolute value is for sure positive. And this is for sure positive. In the middle, it could be positive, which means it will match with the left side, and it could be negative, which means it will match with the right side. Now I can add, if I add on all three sides of this inequality, if I add absolute value an, I end up with, on the left, 2 absolute value an, in the middle, absolute value an plus an, and on the right, 0. So you can stop for a second and see that this is correct. Usually when students of mine see me handling two inequalities at the same time, it's kind of challenging. So one thing you can do to make it easier is just treat one inequality at a time. So forget about this side for a second. Just look at the two terms on the left, add the absolute value an, you see that it's the same, and then do the same and forget about this side. Forget about this side, look at the inequality on the right, and you can see that adding absolute value an makes it a true inequality. Okay. So how's that help me, right? How does that help me? If this converges, then so does this. Of course, it's just double the limit of Sn. This series in the middle, this is convergent, this is 0. This series in the middle then has to be a series of positive terms, right? The ANs alternate between, the absolute value of AN alternate between the positive and the negative version of this. And so the worst case scenario here is these two canceling out, giving me a 0. There's no way I could get a negative. So the series in the middle is always non-negative, right? I said positive, but it could be 0 at times. So by the comparison test, direct comparison, you can say the same about this new series. So this new series also converges. And because we have two convergent series, adding, subtracting them always ends up giving us a convergent series. If you take this series and add to, or I guess subtract is easier. You can say absolute value an plus an minus absolute value an, combine them into 1. Move this down to finish my proof. This also converges. So whenever a mathematician finishes their proof, you draw a little square here on the bottom right, or use some other symbol to say so. This was some sort of math gymnastics that we did here in this proof. All we showed was that if absolute value of an as a series, as a new series converges, then the original series without taking absolute value also converges. So there's no way to go back to the definitions to clarify, solidify. The one without absolute values converges if the one without absolute values converges and the one with absolute values diverges, then we say your series is conditionally convergent. If the one without absolute values converges and the other one also converges, then we have your series is absolutely convergent. But there's no way that you'd have the one without absolute values converge, the one without absolute values diverge, and this one converge. So let me write this again. So it is impossible for this to diverge if this one converges. This is basically what I showed. And so they're not 4 options. There's 3 options, right? Either both of the series with and without absolute values converge, either both of them converge, either right, that's right, yeah. Either both of them converge, and for that I only need to check this, because if this one converges, then for sure this one will also converge by the theorem. Either this one converges, but then this one diverges, and so that's conditionally convergent, or both of them diverge. There's no fourth option in which this one diverges, this one converges. It's not possible. Okay, so let's work on the examples here, see what's the approach for solving these problems. Look at the statement of the problem here. Let me crop this and scroll back up a little bit so you can see this is slightly different from the ones that you've seen before. I'm not asking whether the series is just convergent or divergent. I'm asking, is it absolutely convergent? Is it conditionally convergent? Or is it divergent? So now there's three options they got to choose from, and that may have you, may force you to check multiple possibilities. So the first possibility that I check, generally speaking, I think it's easier to check for absolute convergence, because that allows me to immediately get rid of any alternation, make my series a series of positive terms. So on this series, the ANs are -1 to the power -1, 1 over n to the power 4. So the absolute value of the ANs are the absolute values of this. All that happens with these terms when I take absolute values is that the alternation goes away. The -1 to whatever power just becomes 1 every time. And this is 1 to the power 4. And so that means the series with absolute values is the same. And of course, now I'll show you the bounds for n there. This is a p series, p equals 4, so it converges. The series converges. Because the series converges after taking absolute values, then we say that it's absolutely convergent. The original one also has to converge because of the theorem I just showed you. So we say that the old series is absolutely convergent. So because after taking absolute values, it still converges. So it's absolutely converges doesn't mean that the series for sure converges. That's not what it means. It means it converges absolutely in absolute values. Let me work on B now. So B, you can immediately tell that, or can you immediately tell? Take a look at B. Can you immediately tell something? By taking the absolute values, what are your ANs here? Your ANs are and your absolute values of AN are just getting rid of the -1s. And you can see immediately that the limit as n goes to infinity is 1/2. Again, you can show work on this, which is not 0. So there's no chance that this is convergent in absolute values, but also no chance that this is convergent without absolute values from the discussion we had about the alternating series test. If the ANs, so these are actually the BNs for the absolute values of the ANs are the BNs from the alternating series test, and these don't go to 0. Multiplying by -1 or by 1 won't make it go to 0 either way. So we can say that the series diverges, simply diverges by the test for divergence. There's no need to check for anything. Let's see now. Does this thing converge or does it diverge? Think about it. So if I go and take an is -1 to the power n 3n plus 1, if I take absolute values, I will end up with just 1 over 3n plus 1. And this is giving me harmonic series vibes. You can see that it's very similar to 1 over n in some sense. So this is giving me harmonic series vibes. I think this is probably divergent, so I just gotta draw up a strategy to prove it using the tests that we already know. I think the limit comparison test is probably the easiest way to handle this. Yeah, I can also say that. You can also see a direct comparison. If you don't want to be using the limit comparison all the time, you can see that n is greater than or equal to 1 all the time. So this whole denominator is bigger than this whole denominator, which makes the whole fraction less. So this is 1 over 4 times 1 over n, like this. Say because of the harmonic series or P series, the series with absolute values will diverge. And now, unfortunately, we're starting at 0. That doesn't matter. The starting point for convergence or divergence doesn't matter. That only changes the sum of the series. Now, unfortunately, that doesn't help us much. That shows us that the series is not absolutely convergent, because after taking absolute values, it will diverge, but it could still converge before taking the absolute values. That's allowed behavior, and so we just got to go and check. And this one, because it gave me harmonic series vibes, adding the -1 to the power n here, I think will make it converge just like the alternating harmonic. So I got to go ahead and prove it. So I'm going to take the alternating series test to show that this one converges. So I'll take Bn equals 1 over 3n plus 1. I'll take f of x equals, I don't need to do that. This is very obvious. I have a constant divided by something that grows. So this is clearly decreasing, and also its limit is 0. This is also clear. Again, whenever I have a constant involved, I don't need to be proving things too much. Just always check with your professor if that's not me, but this is clear enough to me by the alternating series test. The given series converges. So because it converged before taking absolute values, but after taking absolute values it diverged, we can say it is conditionally convergent. The last one. So it can be a little scary when we're looking at it, because I have cosines. I have cosines of n. You can say cosine of 1, cosine of 2, cosine of 3, cosine of 4, cosine of 5. This is going to be positive at times. It's going to be negative at times. So what do you do about it? So because your ANs are cosine of n over 3 to the power n, taking the absolute value of an doesn't really make it immediately simpler, but it immediately tells you that this is less than 1 over 3 to the power n, because cosine can never be more than n, right? And this is, on the right, is geometric, with ratio 1/3, which is less than 1. So what does that mean? By the comparison test, because this is bigger, it converges, it forces the other one to also converge. This series right here with absolute values converges. And this means that the original one, without taking absolute values, converges absolutely. Again, it doesn't mean converges for sure. It means that converges even after you take absolute values. And of course, without taking absolute values, it'll also converge because of the theorem that I just showed you.